Namaste. Welcome to the topic on Global Positioning System or GPS, an essential technology in modern geospatial science. Imagine a globe representing our entire planet with satellites orbiting above the Earth's surface. These satellites form a network that allows us to pinpoint our exact location anywhere on land, sea, or air. Think about a traveler looking at a map or the sky, asking fundamental questions like where am I? How do I get to my destination? These questions are as old as humanity itself. And today, GPS provides instant answers using advanced technology. In daily life, GPS touches everything from finding direction on smartphones to tracking vehicles, supporting emergency services, and enabling scientific exploration. As we explore in this video, you will understand how GPS works, why it matters, and how it is revolutionized geospatial technologies. Since the dawn of humanity, people have needed to know fundamental things. Where am I and how do I get to my destination? Finding reliable answers to these questions has driven innovation in navigation throughout history. Early humans, the Stone Age people, relied on natural landmarks like distinctive mountains, trees, or rivers to find their way, perhaps leaving trails of stones and so on. Seafarers initially navigated by keeping the coastline in sight. As exploration expanded across vast oceans, the Star Age of navigation emerged. Sailors learned to use the positions of sun, moon, and stars. The relative position of stars and constellations appear different from different locations on the Earth. Key inventions during this period were a magnetic compass, which always points north, providing the sense of direction, and the sextant, which allowed sailors to measure the angle of celestial bodies above the horizon to determine their latitude and north-south position. However, accurately determining longitude or east-west position remained a significant challenge for centuries. The next major leap came with the radio age in 20th century, particularly spurred by developments during World War II. Ground-based radio navigation systems were developed for ships and airplanes. These systems used radio signals transmitted from towers at known locations. By measuring the time it took for signals from several towers to reach receiver, the user could calculate their distance from each tower and determine their position. However, ground-based radio waves have limitations in terms of accuracy and coverage, especially over vast oceans or remote areas. This led to the satellite age. The idea was to place radio transmitters on satellites orbiting the Earth to provide wider, more consistent coverage. An early system called Transit became operational in 1964. It used the Doppler effect of satellite signals to calculate position, but it was slow, taking about 15 minutes for a fix. It did not have precise timing capabilities on board the satellites. The limitation of earlier system led to United States Department of Defense or DoD to develop much more advanced satellite-based system, primarily for military positioning, navigation, and targeting. This system required high accuracy and incorporated stable atomic clocks on satellites for precise time measurement. This system was officially named NavStar or Navigation System for Timing and Ranging, but it's commonly known worldwide as the Global Positioning System or GPS. The first GPS satellite was launched in 1978 and the consumer devices started appearing in mid-1980s. The system is continuously maintained and upgraded with newer satellites. So what is GPS system altogether consist of? It is a network of satellites orbiting the Earth that continuously transmit coded radio signals. GPS receivers on the ground, at sea, or in the air detect these signals and use the information encoded in them to calculate their precise location anywhere on Earth. The GPS system consists of three main segments. The space segment comprises of constellation of at least 24 satellites orbiting the Earth at an altitude of approximately 20,200 kilometers. They arranged in a specific orbital plane to ensure that at least 4 satellites are visible from almost any point on Earth at any time. Each satellite orbits the Earth about twice a day and carries highly accurate atomic clocks. The control segment consists of global network of ground facilities, including a master control station, monitoring station, and ground antennas. Master control station analyzes the tracking data to determine satellite orbits and clock errors, and ground antennas upload this corrected information back to the satellites. This ensures the satellites are broadcasting accurate information about their position and time. The user segment consists of anyone with a GPS receiver. maybe military users, civilian applications in surveying, aviation, or maritime navigations, agriculture, recreation, countless other users. The GPS receiver receives signals from the satellites and uses the information to calculate its own position. Let us understand how GPS receiver figures out exactly where you are on the globe. The key principle here is measuring how far a receiver is from several satellites at the same time using the radio waves those satellites send out. Since radio waves move at a speed of light, the receiver can calculate how far away a satellite is by timing how long it takes for satellite's signal to reach it. Each signal from a satellite includes two important pieces of information: the satellite's precise position in space, called ephemeris data, and exact time the message left the satellite thanks to the very accurate atomic clocks in the satellite. The GPS receiver also notes the moment it receives this message using its own clock, which isn't as precise as satellites, but it's still good enough for this calculation. By comparing the time the signal was sent with the time it was received, the receiver finds out how long the signal traveled. Multiplying this time difference by speed of light gives the distance from the receiver to the satellite. The whole process is called trilateration. Think of it as like this: if you only know you are a certain distance from one satellite, all you know is that you are somewhere on a huge imaginary sphere that with the satellite at its center. Add a second satellite and measure the distance to it. Now you know that you must be somewhere on the circle where two spheres overlap. Get the distance to a third satellite and the overlap narrows down to just 2 points. Usually one of those points will make sense on Earth. By using these distances, your receiver can figure out exactly where you are in terms of latitude and longitude. In addition to finding out your position in space, GPS receiver needs to correct for its inaccuracy in its own internal clock. By receiving a signal from a fourth satellite, the receiver can solve for both precise location and the exact time, making your positional calculation highly accurate and reliable. This same process happens every time you use GPS on your phone, helping you to find your way, whether you are navigating across the town or hiking in the wilderness. That is why GPS is so accurate and useful in everyday life. While GPS is made to give very accurate positions anywhere on Earth, the location your GPS shows can still be off, sometimes by a few meters. In the worst cases, errors can be as much as 50 to 100 meters, but most modern GPS devices usually get within 15 meters, which works well for daily use. One big reason for errors is atmospheric delay. GPS signals have to pass through the Earth's atmosphere, including layers called ionosphere and troposphere. These layers can slow the signals down a bit, making the satellite seem further than it really is. Since weather and atmospheric conditions keep changing, this delay adds unpredictable errors. Another cause is satellite orbital errors. Satellites send their positions, but sometimes these positions are little bit off. Ground stations fix them, but small mistakes still happen. The receiver's own clock also can cause errors. It is not accurate as the atomic clocks on satellites, and though the system uses extra satellite to fix this, tiny timing mistakes remain. Multipath error happens mostly in cities where signals reflects from buildings or cliffs before reaching the receivers. The reflected signal takes longer and confuses the receiver. Satellite geometry also matters. If satellites are close together in sky, errors gets worse, but when they are spread apart, accuracy improves. Lastly, altitude or height measurements are usually less accurate than horizontal positions because of how satellites are positioned above Earth. Beyond the main error sources, other factors also influence GPS accuracy. The receiver needs to track at least 4 satellites simultaneously to calculate full three-dimensional position and to correct its internal clock errors. The health and operational status of satellite also matter. If a satellite is malfunctioning or temporarily unavailable, it may reduce accuracy. Signal strength and quality can be weakened or blocked by obstacles such as dense foliage, buildings, tunnels, or underwater conditions, which limits GPS functionality. Radio frequency interference from other electronic devices can also degrade the signals and cause inaccuracies. Historically, the US military used a feature called selective availability, which deliberately degraded GPS signals available to civilian users for security reasons. However, this feature was turned off in the year 2000, resulting in a significant improvement in GPS accuracy for everyone worldwide. Overall, the interplay of all these factors defines the quality and precision of GPS positioning that we rely on daily, whether it is for navigation, surveying, or various scientific or commercial applications. Understanding these accuracy factors helps us to appreciate the incredible technology behind GPS and its limitations. To improve GPS accuracy, several methods can be used to go beyond standard consumer GPS receivers. One effective approach is the use of differential GPS or DGPS, which employs a network of fixed ground-based reference stations to broadcast corrected signals, significantly reducing errors and bringing accuracy down to within few meters or even centimeters. Additionally, technologies like real-time kinematics or RTK systems can deliver even greater precision, especially for surveying applications. Other improvements include using augmentation systems like VAS or Wide Area Augmentation System, which provides extra correction data. There are similar regional systems around the world to provide such services to navigation, ensuring a clear view of sky and minimizing obstacles that might reflect signals can also help to enhance the positional accuracy of GPS readings in everyday situations. When it comes to different types of GPS, let us begin by understanding that GPS receivers comes in different forms, each designed for a specific purpose and offering different levels of accuracy and capability. Generally, GPS units can be grouped by grades depending on their intended use and precision. Recreational grade, mapping grade, differential GPS or DGPS and or survey grade. These categories range from simple handheld units used for outdoor navigation to advanced instruments required for professional surveying. The choice of GPS receiver depends on what you need to do, whether it is just finding your way during a trek or collecting important mapping data for city planning or carrying out highly accurate engineering surveys for construction, etc. Recreational grade GPS receivers are perhaps the most familiar type of GPS device for many people. They are handheld GPS units used by hikers, geocachers, boaters, or anyone looking for straightforward navigation outdoors. Their design focuses on ease of use, speedy location fixes, and affordability rather than very high levels of accuracy. Typically, these units provides a positional accuracy of less than 15 meters under open sky conditions, which is good enough for personal navigation and outdoor activities where extreme precision is not needed. Many newer methods can further improve their accuracy down to up to 3 meters, where they can use correction systems like VAS or wide area augmentation systems. While recreational GPS receivers may not be suited for tasks requiring mapping within a meters or less accuracy, they are reliable and versatile choice for adventure, travel, and general exploration. Mapping grade GPS receiver represent a step up in complexity and capability compared to recreational units. These receivers are designed specifically for professional data collection and mapping projects such as for environmental research, city planning, and utility management. They are commonly used by government agencies, researchers, and companies who need more accurate locational data than recreational GPS. Mapping grade GPS receivers use differential correction either in real time or through post processing, which enables them to record position accurate to within meters or even less. In addition to better accuracy, these devices often lets user to collect more detailed information such as recording mapping features, entering descriptions, and integrating with geographic information systems, and so on. This combination of accuracy and data handling makes a mapping grid GPS receiver invaluable whenever detailed data and trustworthy spatial data is needed. Survey grid GPS receivers are most advanced and high precision devices in the GPS family. They are commonly used by professional surveyors, engineers, and in construction projects where the high accuracy is absolutely necessary. These receivers utilize specialized measurement techniques, including tracking both the satellite signals code and carrier phase, along with advanced real-time correction methods like RTK. Using RTK, a base station and one or more rover receivers communicate in real time, allowing the rover to achieve positional accuracy within few centimeters, often between 1 to 5 centimeters also. Survey grid GPS is essential for highly demanding tasks such as defining property boundaries, guiding machine control in constructions, or monitoring very precise movement in engineering studies, and so on. Though these systems are expensive and require training to use properly, their ability to deliver pinpoint geographic information makes them the standard for any applications where location or accuracy matters most. Differential GPS or DGPS is an enhancement of basic GPS technology designed to provide greater accuracy. DGPS works by using two GPS receivers, a fixed base station positioned at precisely known location, and another mobile receiver called rover that is out in the field. The base station continuously calculates its own position using satellite signals and compares it to the true known coordinates. It then sends corrections for any errors it detects, such as those caused by atmospheric delays or satellite orbit uncertainties. The rover receiver picks up these corrections and applies them to its own calculations. Because both the base and rover are in the same general area, the errors affecting both the units are very similar. Corrections from base greatly improves the rover's accuracy. In practice, GPS can improve positional accuracy dramatically, bringing it down to a few centimeters. This level of precision is extremely valuable for navigation in harbors, precision agriculture, and vehicle tracking, as well as mapping where standard GPS is not accurate enough. DGPS corrections can be applied in real time or can be processed later with additional software also. So far, we have mainly looked at the US operated GPS system or United States operated GPS system, also called Navstar. But GPS is not the only global navigation satellite system or GNSS used in the world. Alongside GPS, Russia operates GLONASS, which also has a network of satellites providing global coverage. GLONASS became operational in the year 1990s and works much like GPS, though satellites follow different orbits. Many modern GPS receivers use multi-GNSS, meaning they can use both GPS and GLONASS signals together, giving us better accuracy in places where building, trees, or mountains may block signals. Europe is developing Galileo, a system designed to give very high precision and to work independently, but it also connects smoothly with GPS and GLONASS. Galileo plans multiple services, including a free one for everyone and even a special plan for search and rescue services and highly confidential government services as well. China has its own Baidu system, already giving wide coverage, while India developed Navik, designed to provide very accurate positions over India and nearby areas. Japan has a QZSS, which strengthens GPS performance over its region. Together, all these systems are making navigation more accurate and dependable worldwide. Modern devices combine signals from several satellite systems at once, helping people everywhere in the world. Today, GPS has become an essential part of modern life and is used by a wide range of people, from scientists and engineers to farmers, drivers, surveyors, and emergency responders, and so on. We rely on GPS technology for everyday tasks such as navigation in our phones, vehicular trackings, mappings, and even precise timing for various systems. Its accuracy and convenience have made work more productive, safer, and faster in many fields. However, GPS does have some limitations. The signals from GPS satellites require a clear line of sight to reach the receiver, which means GPS often does not work well in indoors, underwater, undergrounds, or in tunnels, and so on. Tall buildings, dense forests, or mountains can also block or reflect signals, leading to errors or complete loss of positional information. In addition, while GPS provides coordinates based on a global reference system, sometimes these coordinates need to be converted into local systems used in mapping or surveying. GPS is also less accurate when measuring heights compared to horizontal XY positions. Despite these challenges, GPS remains world's most widely used positioning and navigation system. Ongoing improvements continue to make it more reliable and useful in ever-growing number of applications. Today, GPS technology is an essential tool that reaches far beyond its original military purpose. It plays a vital role in everyday lives of many people and professionals around the world. GPS now helps us to find our way when we are driving, track delivery vehicles, plan construction projects, and even keep our power and internet networks working in sync. From agriculture and forestry to public safety and scientific research, GPS allows work to be done more accurately, productively, and often with less effort. Whether you're hiking in mountains, or a farmer checking their crops, or a scientist collecting data in field, GPS makes it possible to determine exactly where things are and how to get where you want to go. One of the major application of GPS is surveying and mapping. In the past, surveyors relied on tools like theodolites or measuring tapes, which required a lot of time and manual effort. Today, GPS, especially when using methods like DGPS or survey grid systems, has made it faster and easier to collect accurate positional data. Surveyors can quickly obtain latitude, longitude, and height of points of interest and then upload this data directly into mapping or drawing programs or GIS softwares. This has revolutionized the way control points are set, topographic maps are made, and infrastructure projects are planned. It means survey and mapping teams can work efficiently even in tougher weather or remote locations with fewer site visits and more reliable or dependable results. The core strength of GPS is its ability to tell us exactly where we are, including our latitude, longitude, and even our height above sea level. This information is vital for many applications, from simple navigation to scientific studies that require accurate positions. Although GPS provides an initial measurements known as ellipsoidal height, which has to be converted for use in some type of mapping and surveying, it still offers very precise method measuring location and altitude. This capability is what allows scientists, engineers, and other users to rely on GPS for planning, exploration, and research. Vehicle tracking is another major area where GPS is used every day. When a GPS device is installed in a car, truck, or bus, its location can be monitored in real time by a control center. This is extremely useful for companies managing fleets of delivery trucks, emergency services like policing or ambulance dispatch, and public transport providers, and so on. The GPS system sends location data through mobile networks or satellites, letting managers to see where every vehicle is on on a digital map. This improves safety and saves time, helps to prevent theft, and allows for faster responses in emergencies and when making deliveries also. Perhaps the most familiar use of GPS to many people is navigation. GPS is now built into most smartphones and is a key feature in many vehicles, boats, or airplanes. Navigation systems use GPS to provide us with a clear turn-by-turn directions, help us to calculate arrival times, and keep us updated about our route as we travel. Whether you are driving in a new city or hiking in a trail or sailing across sea, GPS makes it easy to find your way and avoids getting lost. Today's navigation systems rely on GPS to give users the confidence to travel anywhere. Beyond locations and directions, GPS also helps to keep the world's clocks perfectly synchronized. The satellites in GPS network have extremely accurate atomic clocks on board. Devices on the ground use GPS signals to reset their own internal clocks, ensuring everything from the internet and cell phone networks to bank transactions and power grids runs smoothly. Every scientific instrument that measures time or events use GPS to achieve the highest level of synchronization. This precise timing ensures our communication systems, financial transactions, and even scientific experiments operate reliably and efficiently around the world. GPS has become a more powerful tool in many areas, making work more accurate, efficient, and sometimes even possible where it was not before. In surveying and mapping, GPS allows quick measurement of locations and helps to create digital maps, making it easier for mark boundaries, design roads, and collect data for geographic information systems. In agriculture, GPS guides tractors for planting, fertilizing, and harvesting with greater precision, which increases crop yields and reduces waste. Utility companies use it to map networks of pipes or cables, helping with maintenance and repair work. Vehicle tracking depends on GPS too, letting companies follow delivery trucks in real time, improve routes, and keep drivers safe. Emergency services like policing, fire, and ambulances use GPS to reach incident place faster. Navigation on phones, cars, planes, and boats relies on GPS every day, while public safety benefit from disaster management and search and rescue operations. GPS also provides timing for internet, power grids, and financial systems and is used in recreational for hiking, sporting, and several activities. Truly, GPS touches almost every part of our modern life. Thanks for watching. Namaste.